Proxima Centauri, the closest stellar neighbor to our solar system, has long intrigued astronomers. This Dominion-Ivered dwarf, identified in 1915 by Scottish astronomer Robert Innenis, is part of the Alpha Centauri system, which also encompasses Alpha Centauri A and B. Despite its proximity, just 24 light-years away, it remains invisible to the unaided eye due to its relatively low luminosity. However, Proxima Centauri holds immense scientific significance, particularly as the host star of Proxima B, an exoplanet situated within the star habitable zone. Red dwarfs like Proxima Centauri are smaller, cooler, and have significantly longer lifespans than stars like our Sun. Their low luminosity makes them challenging to observe, but it also means their habitable zones are much closer to the star 4. Proxima Centauri, this translates to an orbital distance of just 0.4856 astronomical units, a mere fraction of the distance between Earth and the Sun. This close proximity exposes Proxima B to intense stellar activity, including frequent solar flares and high levels of radiation, creating an environment starkly different from Earth's. The discovery of Proxima B was a monumental achievement in exoplanet research. Using the radial velocity method, astronomers detected subtle wobbles in Proxima Centauri's position caused by the gravitational pull of an orbiting planet. These wobbles allowed scientists to estimate the planet's mass and orbital period. In 2016, the European Southern Observatory officially confirmed the existence of Proxima B, marking a breakthrough in the search for potentially habitable worlds beyond our solar system. While ground-based observations have provided valuable insights into Proxima B, they come with significant limitations. Atmospheric distortion and light interference hinder the ability of Earth-based telescopes to capture detailed data about the planet's surface or atmosphere. Most of the information we have, such as its mass distance from the star and orbital characteristics, relies on indirect measurements to uncover deeper truths about Proxima B's environment and its potential for life. More advanced observational tools like the James Webb Space Telescope JWST are indispensable. Proxima Centauri's role as a gateway to understanding exoplanetary systems cannot be overstated. As the closest star system to Earth, it offers a unique opportunity to study the conditions necessary for life. Proxima B, in particular, represents a tantalizing possibility. A rocky, Earth-sized planet with the potential to harbor water and perhaps even life. However, the challenges posed by its harsh environment make it a complex puzzle for scientists to solve. The James Webb Space Telescope, JWST, is not just another tool in the arsenal of astronomy. It is a revolution designed as the successor to the Hubble Space Telescope. JWST was envisioned to address the limitations of its predecessor and push the boundaries of human knowledge. While Hubble has provided invaluable insights into the cosmos, its capabilities are constrained by its focus on visible and ultraviolet light. JWST, in contrast, is built to observe the universe in infrared wavelengths, allowing it to peer through cosmic dust and uncover phenomena invisible to Hubble. One of the key design features of JWST is its primary mirror, which spans a staggering 5 meters in diameter, more than double the size of Hubble's mirror. This larger mirror enables JWST to collect far more light, making it capable of observing extremely faint and distant objects. Coated with a thin layer of gold to enhance its infrared reflectivity. The mirror is composed of 18 hexagonal segments that work together to create a highly sensitive observational platform. Another groundbreaking innovation is JWST's 5-layer sun shield, which keeps the telescope's instruments at a constant temperature of about 233 degrees C. This ultra-cold environment is crucial for detecting faint infrared signals without interference from the telescope's own heat. Unlike Hubble, which orbits Earth, JWST operates from the second Lagrange point L2 a stable position approximately 1.5 million km from our planet. This location minimizes interference from Earth's heat and light, allowing JWST to maintain continuous observations. The telescope can study everything from the earliest galaxies to the atmospheres of exoplanets like Proxima B. Its focus on infrared light is particularly significant as it allows astronomers to study phenomena that are red-shifted objects whose light has been stretched to longer wavelengths. As the universe expands, JWST's capabilities extend far beyond mere observation. It is designed to answer some of the most profound questions in science, including the origins of galaxies, the formation of stars, and the conditions that might support life on other planets. With its state-of-the-art instruments, including a near-infrared camera (NR-CAM), the mid-infrared instrument MIRI, and the near-infrared spectrograph (NISP), JWST is not just a telescope. It is a time machine, a laboratory, and a beacon of ingenuity. Proxima B has captivated scientists and the public alike as a potential second Earth. Situated within the habitable zone of its star, the planet has the right conditions to potentially support liquid water, a key ingredient for life as we know it. With a mass roughly 17 times that of Earth, Proxima B is likely a rocky planet. Similar in composition to our own, its proximity to Earth, just over 4 light-years away, makes it an ideal target for studying the potential for life beyond our solar system. However, Proxima B is far from a perfect twin of Earth. One of its most striking features is that it is tidally locked, meaning one side of the planet is in perpetual daylight while the other is in eternal darkness. This creates a unique environment with extreme temperature differences between the two hemispheres. The region where day meets night, known as the Terminator line, may offer a narrow twilight zone with conditions moderate enough to support life. The challenges posed by Proxima B's environment are significant. Its host star, Proxima Centauri, is a red dwarf known for its intense solar flares, which can emit bursts of X-rays and ultraviolet radiation. These flares could strip away the planet's atmosphere over time, exposing its surface to the harshness of space. If Proxima B retains an atmosphere, it likely requires a strong magnetic field to shield it from radiation. Without such protection, the surface environment would be hostile to life as we know it. Despite these challenges, scientists are optimistic about the potential for life on Proxima B. The planet's position within the habitable zone suggests that liquid water could exist, either on its surface or in subsurface reservoirs. Life might adapt to the harsh conditions, much like extreophiles on Earth, organisms that thrive in extreme environments such as deep sea, hydrothermal vents, or high radiation zones. These adaptations could include radiation resistance, subsurface habitats, or unique biochemical processes. The search for life on Proxima B is more than just a scientific endeavor. It is a quest to answer one of humanity's oldest questions. Are we alone in the universe? Proxima B represents a tantalizing possibility. A rocky Earth-like world that might harbor the conditions necessary for life. As our technology advances, so too does our ability to explore this intriguing planet and uncover its secrets. While Proxima B presents tantalizing possibilities, its environment is profoundly shaped by the nature of its parent star, Proxima Centauri. Unlike our Sun, Proxima Centauri is a red dwarf star, smaller, cooler, and far less luminous. Due to its reduced size and temperature, the habitable zone lies much closer, drawing Proxima B into an orbit roughly 0.0505 astronomical units away, approximately 20 times nearer than Earth's orbit around the Sun. This closeness introduces a unique array of difficulties for both the planet and any potential life it may sustain. A primary concern is Proxima Centauri's heightened stellar activity, particularly its vigorous and frequent solar eruptions. These flares are abrupt, potent discharges of energy that unleash substantial amounts of X-rays and ultraviolet light. Compared to stars, like our sun-red dwarfs, generate these flares more often and with greater intensity. For Proxima B, this results in continuous exposure to high-energy radiation, which could gradually erode the planet's atmosphere. Without a protective magnetic field, any existing atmosphere would be vulnerable to being stripped away, leaving the surface bare and exposed to dangerous radiation. Even if some atmospheric layers endure the intense radiation from Proxima Centauri presents serious hurdles for the emergence or survival of life, ultraviolet radiation at high levels can sever molecular bonds, obstructing the creation of complex organic structures. This would severely hinder the likelihood of life developing or thriving on the surface. On Earth, resilient microbes, such as Deinonychus radiodurans, have evolved to withstand radiation by repairing DNA damage, implying that life on Proxima B, if it exists, might have developed similar or even more advanced survival strategies. However, the degree of radiation resistance needed would be extraordinary, possibly requiring entirely unfamiliar biochemistry. Interestingly, the tidally locked nature of Proxima B might offer certain advantages. While one hemisphere continually faces the onslaught of stellar radiation, the perpetual night side might serve as a shelter. Underground environments or deep planetary caverns could protect potential life forms from radiation. Likewise, if Proxima B harbors subterranean OCE, these could act as sanctuaries, offering stable, shielded environments similar to the hydrothermal ecosystems found on Earth's ocean floor. Despite the considerable obstacles, researchers remain hopeful that Proxima B's harsh landscape presents a valuable chance to study how life could survive in extreme environments. Exploring the potential resilience and adaptability of organisms in such conditions enables scientists to expand their understanding of habitability criteria across different worlds. Proxima B is not merely a candidate for extraterrestrial life. It serves as a living laboratory for examining the thresholds of biological endurance. Its relative closeness to Earth and location within its star-habitable zone make it a prime subject for ongoing investigation. With the advent of next-generation space observatories and tools, astronomers are better equipped than ever to study this intriguing planet for signs of life-supporting environments, although significant challenges lie ahead. Proxima B offers a compelling preview of the kinds of life-supporting conditions that might exist elsewhere in the galaxy. It reminds us that the pursuit of cosmic knowledge and the search for life beyond our planet is still in its infancy. The exploration of life outside Earth is far from complete. The detailed examination of planets like Proxima B plays a vital part in expanding our comprehension of what conditions are essential for life. One of the core reasons Proxima B is so fascinating is due to its Earth-like size and rocky composition, positioning it as an ideal reference point for evaluating the potential habitability of planets orbiting distant stars. Scientists are especially intent on identifying exoplanets that resemble Earth, as these are the most likely to provide conditions suitable for biological activity. To probe further into whether life could exist on Proxima, astronomers are deploying cutting-edge techniques to study the planet's atmospheric composition and environmental traits. One particularly promising approach is transmission spectroscopy. This method involves analyzing starlight as it filters through an exoplanet's atmosphere during transit events. The way light is absorbed reveals the chemical makeup of the atmosphere. By inspecting absorption lines in the light spectrum, scientists can identify specific gases such as oxygen, methane, and carbon dioxide, which on Earth are closely linked with biological processes. Detecting such gases around Proxima B would serve as compelling evidence for the presence of life-supporting mechanisms. In parallel, researchers are investigating whether microbial life might exist beneath the planet's surface. The idea of subsurface life has gained traction recently, particularly with the discovery of extraterrestrials on Earth that survive in what were once deemed inhospitable environments like deep sea vents or highly acidic lakes. If Proxima B harbors underground water sources or aquifers, these could act as protective havens, shielding life from the planet's harsh radiation. The presence of such environments would greatly enhance the likelihood of discovering microbial life, adapted to extreme conditions, much like those found in Earth's deep oceans. Beyond the hunt for life, the study of Proxima B provides a broader opportunity to understand the mechanisms driving planetary systems. Its location within the habitable zone of a red dwarf offers a unique platform to explore how star-planet interactions shape planetary atmospheres, climates, and magnetic environments, all crucial components in determining whether a world can sustain life. For instance, Proxima. Centuries' relentless solar flares could play a significant role in shaping weather dynamics and long-term atmospheric stability on Proxima B. Understanding these influences helps astronomers evaluate the broader conditions necessary for habitability across different types of star systems. Though we are still in the early stages of studying Proxima B, advanced tools like the James Webb Space Telescope allow scientists to probe deeper into its mysteries. JWST's ability to observe in the infrared spectrum will facilitate more refined studies of the planet's surface and atmospheric features, unlocking data that could confirm or rule out its potential to host life. As our comprehension of exoplanets grows, Proxima B will remain a central figure in the quest to answer one of humanity's most fundamental questions. Is there life beyond Earth? Ultimately, the research into Proxima B is not solely about discovering extraterrestrial organisms. It is also a journey toward understanding the universal principles that make a planet hospitable. Gaining insights into the prerequisites for life can help us refine our search for living worlds across the cosmos. The study of Proxima B represents just one chapter in an expansive narrative, our ongoing endeavor to map and understand the vast universe beyond our solar system. Additionally, it provides essential clues about planetary formation and stellar evolution, particularly in systems orbiting red dwarfs. By analyzing their relationship between Proxima B and its host star, scientists can better comprehend the dynamics of closed-orbit planets and the forces that shape their development.